Hello, and thank you for joining us today. My name is Ashley, and I will be your moderator. Today's presentation is brought to you as a part of the LI-COR Environmental Education Fund. The LEAF program helps equip undergraduate college classrooms with research-grade instrumentation that provides a number of benefits to students, faculties, and universities. Today we are going to set up a hands-on experiment with LI-COR senior scientist Tom Avenson. Dr. Avenson will be demonstrating the importance of reaching a steady state between your leaf and the environment before taking measurements with the LI-6400 XT Portable Photosynthesis System. Dr. Avenson has set up an experiment remotely, and Aaron Sathoff, application scientist for LI-COR, is in our greenhouse with the 6400 XT and will be positioning it as we move through today's demonstration. Let's see if we can get a thumbs up from Aaron out in the greenhouse. Are you there, Aaron? There he is. Thanks, Aaron. We'll be able to see what Aaron's doing with the instrument through the video feed today. So today's presentation format is very informal, so feel free to type up your questions at any point during the presentation using the questions pane in your control panel. If you don't see the questions panel, just click the arrow most likely located in the upper right-hand corner of your computer screen. So it should look like this. Let's do a little practice to get our juices flowing before we get started. So go ahead and click inside the questions panel and type, "How is the weather in Lincoln today?" We will give everyone just a couple of minutes to find the panel and type the question. We'll see, there we go. We got a couple coming in here. So it looks like everybody has found it. That's great. So as we move through the presentation, hopefully Dr. Avenson will be able to get all of your questions answered, but just in case he can't, we do have a couple of panelists with us today. We have Shannon Lorio, our Science and Support Manager, and Elizabeth Gordon, a Senior Applications Analyst on the line. So you should have begun to receive some answers about how the weather is here today. So I think we're ready to get started. Oh wait, let's also introduce our LEAF coordinator, Kayla Kemp, with us. She's here to answer any questions you might have about the program, its benefits, and how to implement it at your university. So our session today is titled The Importance of Achieving Steady State. So I encourage you to take advantage of this time with our scientists and support staff and send your questions throughout the webinar. So let's go ahead and begin our demonstration by turning it over to Dr. Avenson. Just give me one moment to do that and we'll be ready to go.
Thanks, Ashley, and welcome everybody. This is going to be pretty fun. As Ashley mentioned, we've got a live experiment set up. And what we want to do today is we want you to feel like you're in a room here with us together. And so, as Ashley mentioned, Aaron is up in one of our labs, and he's going to be manipulating a leaf inside the 6400, while I'm actually going to be running the instrument from our recording studio where I am. And so right now you can see that the LI-6400 X term is up, and you can see that the numbers are flickering around there, and that's because I'm controlling, I'm sitting here in a building, in a room separated from where the instrument is, controlling the instrument, which is a nice feature for those of you who use this as a teaching tool. I'm going to go ahead and minimize that. And just by way of introduction, what we're going to talk about today is the importance of achieving steady state when you're taking measurements with your LI-6400. And so the way this is going to work today is we're going to be doing an experiment, a hands-on experiment, and at the same time, while the experiment is progressing, I have about 5 or 6 slides that I'm going to fill in some background information while the experiment is going. And so we're going to actually go back and forth between the talk and the live experiment. And we really want to encourage you to type in some questions. And some of those questions we'll answer probably written, but we also want you to feel like you're able to type in and get our attention right away. We really want to have a virtual community here during this experiment. So I'm going to go ahead and click back on the instrument so that you can see what's going on. And if for those of you who have used the instrument, this is the new measurements mode. And so what you can see there are the different parameters that the instrument is measuring. So for example, across the top, it's the CO2 reference in sample, the H2O reference in sample. The other thing I like to look at quite a bit is the strip charts. And so I'm going to press my right bracket and pull up. And so you can see here over on the side are we have menus A through H. And so if I'm just going to hit up and choose A. And what that shows is a real-time measurement of photosynthesis as a function of time. And you can see that it's very low because if you look on your screen, the instrument right now is clamped on nothing. And so it's a good thing that there's no photosynthesis because there's nothing in there to do photosynthesis. I'm going to go ahead and scroll down. We can see the CO2 reference and sample, the water values. We can see temperatures that are related to the leaf and the block. There's some other strip charts here. Now what I've done is I've set up this configuration so that we can also measure photosynthesis and conductance as a function of what's called observation. And we're going to set up an auto program here in a minute that's going to take an observation every minute. And so therefore what we're going to be able to see in time is we're going to be able to see an estimate of photosynthesis and conductance as a function of time. And we're going to go ahead and I'm going to do this right now. I'm going to press my right bracket and I'm going to define one more figure here. And so I'm going to go back here. I'm going to choose menu 4 and set up graph. I'm going to scroll down to F, where photo and conductance, and I'm going to select that. And you can see that it's possible to have 3 different plots. So I'm going to go ahead and go down to where it says none, and I'm going to turn that on. And I'm going to choose an XY chart and enter. And I'm going to put up CI. So I'm going to choose on the Y-axis. I'm going to go up. Bear with me. It's up here a few. And I'm going to choose CI, which is the intercellular CO2 concentration within the leaf. I'm going to hit that. And then I'm going to define the x-axis as observation, which is down at minus 35, 1, 2, here. And I'm going to say done, done, done. And if we go back into our strip charts, you'll see that now instead of just 2 figures, we've actually got 3 figures. So when we start the experiment, what we're going to observe is the change in photosynthesis and conductance and CI as a function of time, okay? The other thing that we're going to set up before we start the experiment are some stability criteria. So under F5, you can see here that there are 3 different parameters, 2 of which, photosynthesis and conductance, are the parameters that we're going to be watching in time. The third one is flow, and I'm not really too concerned about that. So we're going to change this to CI. And so you just highlight it and press Edit. And right now it's the variable is flow, so we're going to edit that. And we're going to go, I believe it's up. No, actually it's, yeah, CI. We're going to choose CI, enter, and done. And so now what we're doing is in time we're going to be able to monitor the change in photosynthesis, conductance, and CI. And in terms of stability, what I've set up here is the criteria that I've defined are slopes less than 1. Okay, and that relates to this whole notion of what is a steady state, and we're going to come back to that. Okay, so now let's go ahead and get the experiment started so that in time we'll be able to see some raw data. So I'm going to press OK. I'm going to set up an auto program in F1. I'm going to choose AutoLog2, and I'm just going to name this Bob. You can name it whatever you want. And let's see. So I'll go ahead and expand this. So it gives a summary of what is this auto program going to do. What this auto program is going to do is it's automatically going to take data every 60 seconds for up to 50 minutes. Now this is only a half-hour long webinar, so don't worry about the 50 minutes. And I think that's about it. So the point here is that we're just going to do an auto program where we, oh, wait a minute. Ashley, we've got a question coming in.
Yeah, Todd, we have a question from Emily, and Emily says, sorry, I'm new at this. What is CI?
Ah, great. That's a great question. So, Ashley, can I come back to that? What was the customer's name?
Emily.
Emily, let me come back to that because I'm going to talk about that here in a second, okay? I'll come back to that. Great question. Emily, the reason why I want to come back to is I want to get the experiment started so that we can actually start collecting some data, okay? So I'm going to start this auto program, and if you look on your screen right now, we have not clamped on that leaf yet, but I'll bet Aaron is getting up from his chair right now, and he's getting ready to start clamping on that leaf. And so you should see his hands start fumbling. There they are.
Hi, Aaron.
Fumble away, Aaron. So he's clamping on the leaf. And the other thing I want to point out is on menu level 2, this shows the variables that I'm controlling. So I have the leaf fan going fast. I have the flow rate at 500 micromoles of air per second, and I'm keeping that constant. And I have the CO2 reference controlled at 400 micromoles per mole of air. And that's all I'm controlling. I'm sorry. The other thing is that I have the light intensity at 1,000 micromoles per meter square per second. Incidentally, that plant that Aaron just clamped on, that leaf, was probably exposed to maybe about 100 micromoles per meter square per second. And so what we've done is effectively transition that plant to a very high light intensity very quickly. And what we're going to look at is, over time, how long does it take for these different photosynthetic parameters to reach a steady state. And that's what we're going to talk about today. And so the experiment is going, and so while it's collecting data, we'll come back from time to time, and one of the things that we'll look at is the slope. So if you see here, for example, the slope for photosynthesis is 4, conductance is 1.5 to the minus 2, and we're going to kind of keep an eye on these parameters. And we can also go back and forth, and we can toggle back and forth between the stability and the actual raw data. So this, just remember that when it says obs at the bottom, we're taking an observation every minute, and so effectively this is looking at photosynthesis conductance in CI as a function of time. All right, so let's go and get to some of the questions like Emily just asked. So what I want to do is just provide some background about photosynthesis, leaf level photosynthesis. And so this is a schematic of a cross section of a leaf. So this would be the top and the bottom of the leaf. And inside the leaf are cells, and there are many cells. In this schematic, it's very simple. It's showing a single cell, and that single cell is bounded by a cell wall, a plasma membrane, both of which enclose the aqueous compartment called the cytosol, as many of you, as most of you, I'm sure, know. Now, inside the cytosol, there are many different organelles. But here at LI-COR, we have a very chloroplast-centric view of what the leaf does. And so what's shown here is that this is a depiction of a chloroplast, and it's bounded by a double membrane, inside which is another aqueous compartment called the stroma. Now, within the leaf, there are pores, stomatal pores, that allow exchange of gases between the atmosphere and inside the leaf. Now, stomates impose a certain amount of resistance to the diffusion of these gases, and as a result, the concentration of water inside the leaf, or Wi, tends to be higher than the concentration of water in the atmosphere, or Wa. In contrast, the concentration of CO2 in the atmosphere tends to be higher than the concentration of CO2 inside the leaf. So, Emily, the CI represents the concentration of CO2 in the intercellular air spaces within the leaf. That's what CI is. So that's why I wanted to wait, because I was going to talk about that explicitly. Now, once the CO2 gets inside the leaf, it actually has to move into the chloroplast. And it does so through a convoluted pathway that's referred to as the mesophyll. Now, the mesophyll pathway involves the movement of CO2 across the cell wall, the plasma membrane, the aqueous cytosol, the double membrane of the chloroplast, as well as the aqueous phase of the stroma. And that pathway, that mesophyll pathway, imposes a certain amount of resistance, which is referred to as mesophyll resistance, and it's represented by this resistor here. Now, the other thing that I hope you'll notice is that the concentration of CO2 in the intercellular air spaces, the font size is larger than the concentration of CO2 in the chloroplast, or CC, and that's meant to just depict the fact that because of this resistance, the CO2 inside the chloroplast is not only lower than CI, but it's lower than CA also. Okay, because of these resistances, the concentrations of CO2 that end up in the chloroplast are lower than in the atmosphere. Now, as most of you should know, that the carbon dioxide from the atmosphere is used to make sugars. So depicted here is just a very simple schematic of the Benson-Calvin cycle showing the incorporation of carbon dioxide with RUBP, or ribulose 1,5-bisphosphate, ultimately generating some 3-carbon sugars. The end pathway here is, this point in the pathway is referred to as glyceraldehyde 3-phosphate. And what I've shown here is the incorporation of 3 molecules of CO2 and 3 molecules of RUBP generates a pool of 6 glyceraldehyde 3-phosphates, 5 of which are needed to regenerate the original RUBP. So this cycle, in order to keep it going, the original RUBP has to be regenerated. And so the majority of the triose phosphates that are made at this point are used to regenerate that RUBP, and in the process some ATP is consumed. Now, for those of you who are experts in the carbon assimilation reactions, this is a very simplified schematic. It's just meant to depict the incorporation of CO2 into sugars and the consumption of energy in the form of ATP and NADPH. And in fact, the stoichiometry of these reactions require the 3 ATP per 2 NADPH per CO2 molecule. So that's the stoichiometry. And that'll become important here in a moment. Do we have a question, Ashley?
Yeah, Tom, we have another question from Emily.
Yeah, Emily.
Emily says, so CI is the internal concentration of CO2, yes? If so, then how does that differ from CO2S?
CO2, okay. So that's a great question. So let me go back to, I'm assuming, Emily, that when you say CO2S, you're referring to, let me get to it here, you're referring to CO2R versus CO2S. Okay, so I'm assuming that's what you mean. And the CO2S is the concentration of carbon dioxide that's inside the chamber where our leaf is. Okay, so there's a little microenvironment inside that chamber, and that CO2 that's inside that chamber that's surrounding the leaf, that's CO2S. And the first question was, you were right, that CI. So CA, you can think of in this schematic that CA is CS. Okay, so in our little chamber, the concentration of CO2 surrounding the leaf is the atmospheric concentration in our little atmosphere in there, and CI is the concentration inside the leaf. So great question, and keep toggling those questions in if that wasn't clear.
Thanks, Tom.
Yep. Okay, so we have the Benson-Calvin cycle and we have energy. Well, that energy, as you all know, comes from the sunlight. And what I've depicted here is a thylakoid membrane, embedded in which are all of the proteins and cofactors, and this is again a simplified schematic, but it's showing the absorption of light and the oxidation of 2 water molecules, which results in the oxygen that you and I are breathing right now, by the way, and 4 electrons and 4 protons. Those electrons are transferred through a series of redox intermediates involving plastoquinol, the B6F complex, plastocyanin, and in the process, because of the stoichiometry of the B6F complex, 8 protons are transported into the lumen per the transfer of 4 electrons. Those electrons are subsequently shuttled to photosystem 1, at which point the absorption of light results in those electrons being deposited into NADP, forming 2 molecules of NADPH. Now, this 2 molecules of NADPH per oxidation of 2 water molecules should strike you, because as I said over here, per CO2 assimilated, 2 NADPH are needed. Well, what about the ATP? What about these protons? Well, the oxidation of these 2 water molecules results in 4 protons here and 8 protons at the B6F complex, with a total of 12 protons, generating what's referred to as the proton motive force, or PMF, which consists of both an electric field and a pH gradient. The total proton motive force drives the synthesis of ATP as these protons move down the electrochemical gradient, doing so through the chloroplast ATP synthase, which I've represented here as a resistor, because it imposes a certain amount of resistance to the flux of protons. And what's important about the enzyme is that it has a proton to ATP ratio of, well, it's widely thought to be 4.7 protons per ATP. And what this means is that when these 12 protons are moved down through the enzyme, only 2.1 ATPs are formed, which is a little bit short of what's needed to assimilate a single CO2 molecule. And in the literature, many of you may have heard of a process referred to as cyclic electron flow around photosystem 1, or CEF1. And this augments the proton motive force in order to balance the output of ATP that's needed to assimilate CO2. Now, it turns out that the energetic demand of the Benson-Calvin cycle and other reactions that are occurring in the chloroplasts are saturated at relatively low light intensities. And what this means is that there's a potential for the absorption of excess energy. This excess energy can actually result in the formation of a very wide range of reactive oxygen species, one of which is referred to as singlet oxygen, the other one as superoxide, the superoxide radical. And the plants possess a very extensive protective mechanism, one of which involves a process referred to as non-photochemical quenching, or NPQ. NPQ operates in the antenna of photosystem 2, and it harmlessly dissipates excess energy so that it doesn't result in formation, or so that it attenuates the formation of these reactive oxygen species. NPQ dissipates the excess energy effectively as heat, and the predominant mechanism of NPQ is referred to as QE, or energy-dependent quenching, and it's a function of the delta pH component of the proton motive force, which results in the formation of a pigment called zeaxanthin, and it results in protonation of PS2 associated proteins. So this is all just sort of to give you a introduction to the processes of photosynthesis, many of which that you can measure with your 6400, especially if you have a combined gas exchange fluorometer. If you have a combined gas exchange fluorometer, you can measure virtually 80% of these processes that we talked about. NPQ, electron transfer, obviously with the gas exchange you can measure CO2 assimilation. So the point is that these are the types of processes that you can measure. So let's go ahead and I'm going to go ahead and interrupt myself, and let's go ahead and look at our data real quick. So what you can see here, I'm going to go ahead and scroll up to where photosynthesis. So here is our observations, which is effectively time, because we're doing it every minute, and this is photosynthesis. And what you can see in terms of photosynthesis, conductance, and CI, neither of these things are in a steady state. And steady state would mean that the signal is constant. And we're going to come back to that here in a minute. Let's go ahead and look at the slope of some of these processes. So you can see here that the slope for photosynthesis is fluctuating, but 1.2. So when the system is in a steady state, hypothetically, a precise steady state, the slope should be 0. So that's effectively what a steady state means. So let's go ahead and we're going to let those data continue on for a little bit longer. Let's go back to our talk here. So this is photosynthesis. What can you measure? This is not meant to be an exhaustive survey of everything that you can measure with the instrument, but shown here are some data where they're looking at a diurnal time course of photosynthesis under control, atmospheric levels of CO2, elevated ozone, and elevated CO2 plus ozone. And again, I don't want to go into this exhaustively. This is just showing the diurnal effect of photosynthesis, which tracks which tracks sunlight effectively. So at noon, you're going to have the highest amount of photosynthesis. You can also explore the limitations of photosynthesis using, for example, an ACI curve. This, Emily, by the way, this is a plot of CO2 assimilation as a function of CI, or that intercellular concentration of CO2. And when this experiment is done correctly, it can give information on three main processes that limit photosynthesis, one of which is the enzyme kinetics of Rubisco, some of which involve limitations imposed by electron transfer, and under very high CO2 conditions, triose phosphate utilization can limit photosynthesis. And this information can be obtained from an ACI curve. So that's just a couple examples of the types of information that you can get using the instrument. So I'm going to go back here and talk about this data real quick. So let's go back to, so what you can see here is that in none of these cases is the, actually I'm gonna go back and skip through a couple slides and talk about steady state for a minute. So bear with me. So this is a nice schematic model from Dave Kramer's lab, where he's showing a fluid dynamic model for the steady state proton motive force. And in this fluid dynamic model, what he's showing here is fluid deposited into the bucket, into this can, and that fluid represents electron transfer. The fluid exits that bucket, and he's showing that as the ATP synthase, and so that movement of the protons out through the ATP synthase is coupled to the formation of ATP. Now you have to use your imaginations, because this is not a dynamic, this is a static model, but you have to imagine that steady state involves the influx of this liquid, a constant influx and a constant efflux. However, if we measure the amplitude, the level of the proton motive force, or the level of fluid in this bucket, that level would remain constant. And that is sort of a way of it's analogous to what steady state means. So steady state doesn't mean that there's no flux going in or going out. It means that there's a flux in and a flux out, but they're at rates that keep that such that the amplitude, the level of liquid in the bucket, remains constant. Okay, and so let's go back to our data. So in this case, you'll see that photosynthesis, conductance, and CI. Well, let me go ahead and I didn't plan this, but let's go ahead and ask a question, Ashley. Would everybody say that are any of these parameters in a steady state? Can you guys go ahead and I'm gonna wait for 30 seconds, and we're gonna tally up the votes and see if and see whether or not you guys think the leaf is in a steady state.
Sure. Why don't we just have everyone type their answers into the questions panel, and we'll run through them here quick. We have a maybe and a couple of no's right now.
All right. Aaron, are you still up there? Are you okay? Make sure he's still there. Yeah, he's still there. Okay.
A couple more no's and one that says not yet, but it looks like the slopes are beginning to level.
Let's I'm gonna go ahead and click over.
Lots of no's.
Lots of no's. That's great. That's right, because none of the signals are in a steady state. Because under a steady state, according to this description that I just described, the whatever parameter that we're measuring, it should remain constant. In this case, the fluid within that bucket should remain constant, the level of that fluid in the bucket. Now, with respect to these data, a steady state would mean that the signal was constant. Okay, so what we did is we took that leaf, and it was exposed to maybe 100, and we subjected it to 1,000. And so what you can see, if you're doing an experiment, if you in your lab are doing an experiment, and you want to be able to move quickly through a series of different leaves and reach a steady state, you can see very clearly that if you're going from a low light intensity to a higher light intensity, it takes a lot longer. It takes a while to reach a steady state. And in fact, I'm gonna switch this to a lower light intensity, but it may take upwards of 45, 50, maybe an hour for conductance to reach a steady state. So if you're really wanting to measure conductance accurately with an open flow system, you're going to have to wait a while. So if you're transitioning from a low light to a high light. So let's go back out and let's see what happens going from a high light back to about 100. So I'm going to go ahead and escape out of here. I'm going to go to F5, and I'm going to target 100. So I'm going to switch. So what I'm doing right now is I'm switching the light level within our little microenvironment back to about 100. And let's go ahead and go back, and you'll be able to see. You can see the arrow here for photosynthesis. It's decreasing. I'm going to go to A. So you can see this is a strip chart of photosynthesis in time, and you can see when I turned the light off, photosynthesis very abruptly started to decrease. I'm going to go ahead and go back here to I think it was F. And so what we're going to so while this data is while this data is being collected, we're going to come back to it just like we've been doing. And let's go discuss a little bit more about some other slides here. So let me go back to here. So just to remind you for those of you who may not have been here for our training, the instrument is taking advantage of absorption of water and carbon dioxide in the infrared region in order to measure concentrations of these gases. And so what I'm showing here, I'm sorry, I had this figure animated, but now it's all showing up. So you just have to bear with it. It looks a little messy, but let's just walk through it. So the green lines represent absorption of water within this region 2.49 to 3. And over here in the blue, this represents absorption by CO2 within this region here. Now, in the instrument, we have filters that are transparent to light within this region here for water and within the region for carbon dioxide. And we also have some filters that are transparent to the light in the non-absorbing region for CO2 here and the non-absorbing region for water in this region here. And so in order to measure absorption, if you'll remember, absorption plus transmission is equal to unity, such that absorption is equal to 1 minus transmission. And in our case, transmission is defined as the power detected in the absorbing region for water and CO2 divided by the power detected in the non-absorbing region. So that's transmission. And so this is how we measure absorptions. But how do we measure power? Well, we have a light source within a blackbody light source within the instrument that radiates blackbody radiation. For those of you who remember from chemistry, blackbody radiation is emission of the full spectrum of wavelengths, including the UV and the visible as well as the infrared region. And what I'm showing down here is a schematic of this light source passing through a chamber in which there is a leaf that could be photosynthesizing and transpiring. So there's water inside the chamber and there's carbon dioxide. Now, a certain fraction of this light is within the absorbing region for water. And what you can see here is that light traverses the chamber. It's attenuated, and it's attenuated because it's being absorbed by the water. It exits the chamber and it's focused onto a spinning filter wheel, and this filter wedge is transparent to light within the absorbing region, within this region here. And so therefore that light is able to pass through the detector and be detected as a voltage that corresponds to the power detected in the absorbing region for water. Now this filter wheel is spinning, and so some of this light is also in the non-absorbing region for water. And as it traverses, and actually, I'm going to ask a question. So I'm going to call the width of this blue line how much blue light there is in the blackbody radiation. As that light traverses the chamber, is the width or the amount of light going to remain constant, decrease, or stay the same? So why don't everybody? So is the non-absorbed light going to increase, decrease, or stay the same? Let's go ahead and have people type in what they think about that.
We have 1 vote for constant.
Great.
1 says stay the same.
I would interpret that as constant.
Another same.
Yeah. Well, you guys
Looks
are
like
good.
We're guessing all the same.
Oh, great. That's great, guys, because that's exactly because remember, this is non-absorbed light. So yes, what happens is that non-absorbed light traverses the chamber. It hits. Now, I'm not going to ask the question. Because of time, I'm just going to go ahead and say it, is that this filter wedge is not transparent to this light. And so it doesn't pass through this filter wedge. But this filter wedge is spinning. And the next wedge that is going to come up here is going to be the wedge is going to be transparent to that light in the non-absorbed region. And that's going to allow that light to pass through the filter, hit the detector, and be detected as a voltage that corresponds to the power detected in the non-absorbed region. And so this is how we measure transmission. And based on this transmission, this is how we measure absorbance. And we don't have the time to go into it, but absorbance can be related to the concentration of both CO2 and carbon dioxide. And that can be the topic of another LEAF webinar if that's of interest. But for the sake of time, let's go ahead and go back and look at what's going on with our LEAF. Okay, so you can see here that this is the point at which we clamped onto the leaf. Photosynthesis progressively increased. You can see here, and it wasn't in a steady state at all during that entire time. It was getting there. Conductance was never in a steady state. But you can see here that when we transitioned from that high light to a lower light intensity, that it looks, we still have another, how much time do we have? We have another 4 or 5 minutes. We'll let this go for a little bit longer. But typically when I've done this, the going from a high light to a lower light intensity, the system reaches a steady state. When I say the system, I mean the leaf within the instrument reaches a steady state within 4, 5, 6 minutes. So, and you can see here that CI is starting to stabilize. Conductance is, I'm not sure, it's still kind of changing a little bit. So, so let's go ahead and go back to the. Let's go back to the screen. So this is how we measure absorbance by these gases, which can be related to concentration. Now, in an open flow system, which is what the instrument is, this is a schematic of the open flow system where air is going into the chamber in which there is a leaf. In the case when it's exposed to light, it's going to be taking up carbon dioxide and releasing water. The air exits the chamber. And this is what's referred to as an open system. The mu-I stands for the flow rate of air. Ci, so Emily, don't get confused. I should have changed the nomenclature. We want to change the nomenclature. This should be Ce. So it's the concentration of CO2 entering the chamber. Okay. And once it's in the chamber, Emily, that would be considered CS, or the sample concentration. It's just the carbon dioxide within our little microenvironment. So I apologize for I should have changed it to CE. Okay, sorry, Emily. The other gas that we're interested in is the water mole fraction, which is also going in here. Now, we can define fluxes, and for example, the flux of water going into this chamber can be defined as the flow rate multiplied by the mole fraction. And so here are the units. The mole of air cancel such that we get moles of air per second. So that's the influx of water. We could equally define the outflux of water based on the flow rate out times the water mole fraction out, which gives us moles of water per second. Now, based on these fluxes, we can define generally transpiration, which is the flux of water into the atmosphere, as the outflux minus the influx, using these values here. And furthermore, it's important to realize that the instrument is capable of measuring the incoming flow rate, but it doesn't measure the outgoing flow rate. But it's assumed that the outgoing flow rate is equal to the flow rate that's coming in plus the amount of transpiration that's happening. Okay, and so by substituting this expression into this equation here and doing some algebraic manipulation, and I would highly encourage those of you who teach a course to go through the math and maybe even have your students do that so they understand how these parameters are derived. At any rate, when you do the manipulation, transpiration is defined according to this simple expression here. Now, you can also define CO2 assimilation by another simple expression as shown here. And what I want to emphasize, the whole point of doing this webinar and this experiment today is to emphasize that there are no partial differential equations. There are no derivatives in this equation. So the math underlying estimation of transpiration and photosynthesis by an open flow system like the 6400 is predicated on the system being in a steady state. Okay, so all of these values that are all of the values are assumed to be in a steady state. Now, if we go back to our data, now if you were doing your experiment, you will indeed get a measure of photosynthesis. This value right here, it is a measure of photosynthesis by that equation, but you as a user need to realize that if photosynthesis is not in a steady state, it truly does not reflect an accurate measurement of photosynthesis by an open flow system like the 6400. Now you can see we've waited 1, 2, 3, 4, 5, almost 6 minutes, and you can see that when we transitioned from the high light to the low light, you can see that photosynthesis pretty quickly, much more quickly stabilized than it did when we went from the opposite. Okay, so that should give you some methodological information on how to design your experiment so that you can achieve steady state on a more rapid basis, if that's what you so choose. And you can see here that CI is relatively constant. Conductance is still creeping up here a little bit. But the other thing I want to point out is that in this experiment, I'm not controlling anything. I'm not doing any control of the water. Okay, and so if you really wanted to do this experiment carefully with your students, one thing that you can do is you can control the concentration of water. So for example, H2OS, you can keep it constant. You can control the temperature and keep the leaf temperature constant so that you can keep the vapor pressure deficit across the leaf constant and avoid changes in stomatal conductance. Okay, and so you can do this experiment much more carefully. Now, Ashley, are there any questions?
No, Tom, we don't have any questions right now.
Okay, well, everybody, that's the extent of what I wanted to say today. Just to recap, that steady state is it's an important state because of what's needed, because of the instrument, the 6400 is predicated on the parameters being in a steady state. Number one. Number two, a steady state is just simply that the parameter that you're measuring remains constant as the level of fluid in this bucket, this analogy. And with that, if there are any other questions, or Ashley, I'm going to go ahead and turn it over to you. And what do you need us to do
All
from
right,
here?
thanks, Tom. I think we'll just stick on a little bit longer in case anyone else has any questions.
Can I follow up with Emily real quick? Emily, can you go ahead and just type in real quick whether or not you're clear about what CI is?
Sure, we'll give Emily just a second here.
If you're still there, Emily.
Yeah, let's just say thanks to Aaron while we're waiting for all of his help up in the greenhouse, and thanks to Shannon and Elizabeth for being on the line to answer questions today. And we also have Kayla here, so if any of you have questions about the LEAF program, you can go ahead and send those questions to her as well. So Emily must understand because she hasn't typed in anything.
Okay.
So.
Well, great, everybody. It was nice. It was nice being here with you, and happy researching.
All right. So thank you to everyone for taking the time to participate in our webinar today. We'll be sending information about how to access a recording of this session pretty soon. So watch your email or LI-COR.com/ENV/webinars for details on how to watch that replay. And Emily says right here, Tom, can I email you later with more questions? And I'm guessing the answer is yes.
Of course. Yes, you can email me.
All right. Thank you, Emily. So our panelists are still answering those questions that you're typing in, so stick around if you have any more that haven't been answered. So we'll be taking questions for just a little bit longer, a few more minutes. We have some time yet. So let us know also how we can improve our webinars by answering our post-event survey questions when you exit out of our webinar. We're very interested in receiving your feedback regarding this educational resource and how future webinars like this one that Tom did today might fit into your classroom curriculum or your research. So thank you for joining us today, and we hope to see you at our next session.
Ashley, 1 second.
Yeah.
So I just want to reiterate what Ashley just said, and that is this is the first time I've ever done a sort of live experiment like this, and we really want to explore whether or not this is useful for not only you LEAF folks, but if you have friends that are using the 6400, and this could be a useful way for you to learn about different topics. Please send those topics in and give us an idea of whether or not it was helpful. And we want to explore how to use this effectively.
Thanks, Tom. We just got a couple of comments saying that it's very useful. So
great.
We'll look forward to reading your responses when you close out of the session.
Okay, take care, everybody.
Thank you.